Good evening, everyone. Welcome to today's class on Aspen Hysys. I would like to confirm, or I would like to know if you can hear me. If you can hear me, there are different softwares that is being used or can be used for process simulation. But for this training or for this class, we are treating Hysys. So what is Hysys? Aspen Hysys, the word Aspen is an acronym for Advanced System for Process Engineering, and it is based on a flow sheet simulation. Now we are now going to look at what a flow sheet is. Um, by definition, a flow sheet is a simplified pictorial representation of a process, and it's being used to present um, relevant process information and data. A flow sheet is defined, can also be defined as a diagram that shows the operating unit involved in a process and their interconnections used to indicate the flow of various systems and supplemented by properties such as composition, temperature, and pressure. So the software we are going to be using, which is Hysys, a lot of you know about it, and few of you just know that it's being used in chemical engineering, process engineering, but you don't know how this software operates. So Aspen Hysys is a flow sheet simulator software. And by definition, we say that its flow sheet is a simplified pictorial representation of a process. So how your feed goes in, the process it follows, the path it follows up until the point where you get your final product. That is what a flow sheet looks like. So you have, assuming it's a separation process, you have your feedstock, it goes into your maybe sieve, you sieve it, it goes into uh, another equipment. Maybe you have like 5 different units before you get your final product. Now, a flow sheet shows you that sequence, that step-by-step process you need to follow up until you get your final product. And this is an example of a flow sheet. Now um, we have our feed, and you can see the different composition from our definition. It says a flow sheet is defined as a diagram, which you can see the diagram, that shows the operating units involved in a process and their interconnections used to indicate the flows of various streams and supplemented by properties. Now you can see this interconnection. You can see your mixer here. You can see your heater. You can see your reactor. This is a tank or a separator, a two-way separator. You have another mixer. You have a compressor. You have a translator and all of that. So this is basically a flow sheet, and this is what we will be doing in Aspen Hysys. Now, what is a simulation? A simulation is a computer-based imitation of the real-world process. Okay, so a simulation is a computer-based imitation of a real-world process or system. How do we imitate this? How do we imitate this real-world process? By using mathematical model to mimic test scenarios like what if analysis and train user safely and to understand complex phenomena in science, engineering, and management. So the Aspen Hysys uses advanced thermodynamic model, mathematical equation, and engineering prediction. Aspen predicts how real plants would behave under different conditions. And that's what the simulation is all about. So when you hear that we want to run a simulation of um, an absorber or want to run a simulation of maybe I'm trying to a wellhead or a well gathering system, whatever you want to simulate. Just know that what we are trying to say is we want to use a computer program to mimic or imitate how that system is supposed to run in real life. So if you want to do a separation process or a mixing process, how is that process supposed to run in real life? And as engineers, we can't, in order for you to develop a plant or a functional system, you need equipment, you need manpower, you need time. And going into the field with your equipment, whatever, to do try and error. Now, that's you are going to waste your time. You are going to also damage equipment. You are going to burn manpower. You're also going to burn money. So, what a simulation software does, with the help of some mathematical models, we could use our laptop or system and run these programs to see how this program how this program is going to run in real life. Either you are doing maybe LNG compressor, you want to run a simulation of an LNG plant or cyclohexane plant or cyclohexane production, whatever gas synthesis production or simulation you want to run. So you just know that you are trying to use the software to see how these things is this whatever you want to do is going to play out in real life. And if you are going to get your desired result. So this is where Aspen Hysys flowsheet simulation enables us to run mini tasks such as what if test. So if we are carrying out a cyclohexane production simulation, okay, we can now do what if. What if this happens? What if the pressure we are using this um this gauge? What's going to be our output? We can also do design specification. We can do we can carry out the bottlenecking, we can perform sensitivity analysis, we can run optimization investigation. With Aspen Hysys process simulation, we could design better plans and increase profitability. So, with what I've said, I would like you to drop a comment in the session. How do you think we could use Aspen Hysys process simulation to develop better plans and increase profitability in our existing plants? I would like you to drop your answer in the comment section. Okay, Aspen Hysys process simulation model. We can translate a process into Aspen, supposed to be Hysys, Aspen Hysys process simulation model by performing the following skeletal but necessary steps. The first one is to specify the chemical components in the process. Where you open Aspen Hysys and you have created your first project, which we are going to do during the course of this lecture, one of the first things you need to do is to specify the chemical component. If you want to produce water, we know that we have hydrogen and what and oxygen. It's now we want to do whatever we want to do Hysys to get water, a process to get water. We need to specify the components, our reactants, and the product. So those components that we are going to get, our hydrogen, oxygen, and water, we need to specify those components. And we can fetch these components from the Aspen Hysys database. The next thing we need to do is to specify our thermodynamic model to represent the physical property of the components. We are going to talk about thermodynamic model as we go forward. The next thing we need to do is to define the process flow sheet, define unit operation in the process. Okay. A good question I would like you to answer, a quick one. What's the difference between a unit operation and we have unit operation? There are two operations we have. Unit operation and the second one is I think unit process. Yes. What's the difference? What's the difference between the operation and the process? Then apart from while you are answering that, then define the process stream that flows into um, in and out of each unit operation. Select select the models from Aspen Hysys library. We need to label each unit or each block. We'll specify the component flow rates and thermodynamic condition. We also specify the operating condition for the unit operation. And these are the basic steps we use in carrying out any thermodynamic, in carrying out any simulation we want to do in Aspen Hysys. So while I'm lecturing or teaching, if you have any question, please do not hesitate to drop it in the comment section. Thank you. Okay. Um, application application process applications of process simulation. So um, where can we apply process simulation? Process simulation is a tool for process and chemical engineers that can be used in the execution of repetitive tasks and that must be solved in relatively short time. The various applications that process simulation has found are the result of the necessity of one, making a better use of energy resources, minimizing the operating cost and the emission of waste stream that may be contam that might be a contaminant, increasing the yield and process efficiency, improving controllability, propelling the teaching of process design. So I'm going to go into this a little. Um, these are the areas where we carry out process simulation. And why do we do that? One of the reasons why we do that is to make better use of energy resources. Whenever you are carrying out a process simulation, there are times you have waste. Yeah, most of the time you have waste. Yeah, you have waste. Now, this waste product you do get, sometimes this waste product can be used as energy. So, for instance, you are separating two volatile components, or let's use crude, for instance. You want to get an gas. or you want to get kerosene, for instance. Now, from the products, we know that there are different. There are lots of components of products we can get from the product. Instead of you using maybe a different energy source, maybe electrical power, from the crude, you could use one of those components as your source of energy to heat up or run your generator. So when you carry out your simulation, you are going to know what you are getting as your waste material. Now that will help you. Okay, this waste material we have gotten. What can we use it for? Can we sell this waste material? Is it useful? What is it disposable? Can it be used for something else in the plant? So something that is being used that is being considered a waste to some other company is not a waste. So that waste product you are getting from your process can actually be used as a source of energy. And using it as a source of energy, you are now minimizing the operating costs and the emission of waste. So instead of you to flare that gas, you can now use that gas as an energy source or use it to power your turbine or one in any of your machines. It also is Aspen is useful in a way that increases the yield and process efficiency. Um, I'm going to give this illustration. We have a process, and what we want from this process is to get a maybe 90% purity of our product. So what we have, our feed, we are getting, okay, what we want is 70% purity. We are okay with 70%. With Aspen Hysys, we could run some sensitivity analysis and optimization in a way that we could say, okay, is there any parameter in this flow sheet we could change that can increase the yield of our product? So you might say, okay, with this feedstock we have, if we increase the temperature, what is going to be the output of our product? So you might increase the temperature and find out that you are consuming more energy and your product is still the same. You know that that's not going to work. Increasing temperature in this process will not increase your yield or percentage purity. You can now increase your pressure. If we use, if we move this pressure upward, is it going to increase our yield? Now, with that, carrying out that sensitivity analysis will help you, you know, increase your yield and your process efficiency. So if your product is now, you have a 10% increase in its yield, you find out that you are now making profit from that. Now you also ask yourself, increase in the pressure we increase, did it how did it affect our system? Are we spending more money? Because one another thing you're looking at is also getting profit. So with Aspen Hysys, you could run series of scenarios you get to understand which is optimal for your system, what process, what composition, what thermodynamic property will give you the best yield you want for your process. And it's also it's improving the process controllability, propelling the teaching of process design, basically what you are learning now. And these are the 5 types in Aspen Hysys. So the extension for template is .apt. User model is .apm. When we are talking of templates, we are looking at um, custom settings or files that came in Hysys. The one we are looking at, or that is embedded in Aspen Hysys, these are system files. The one we are looking at user model, these are templates that were customized by the user. We also have input. We also have backup and documents. We also have compound. Most of the time, your files will be saved in APWZ or APW. Aspen Hysys modeling and simulation procedure. So the first thing we need to do is to do our setup. We need to include the titles, the description, purpose of the job. This purpose of the job is optional. Next thing we need to do is to set our units, define chemical components to work with, physical properties and thermodynamic properties of the model. We need to choose the unit operation we are using the blocks and connect our streams, then the simulation. So before we move in, dive in further to start using Aspen Hysys, I would like to know if there is any question from anyone. Does anyone have a question? Okay, so but if you are online, please, uh, I would like you to drop a message on the comment section. Just indicate I'm online. If you are online, please indicate I'm online. Okay, so we don't have any question. Um, this session wasn't intended to be long. We we are going to dive into Aspen Hysys majorly from our next class on Wednesday. Today's session is basically an introductory aspect of Aspen Hysys, the theoretical part explaining the necessary things you need to know. So while we were um, in the introductory aspect, I said I was going to explain what thermodynamic properties, which is what we are going to look at. Now, when we talk about thermodynamic property, what exactly are we talking about? When we say thermodynamic property, what are we talking about? So when we say thermodynamic property, we are looking at thermodynamic properties are measurable characteristics of a system that define its state, such as temperature, pressure, volume, etc. So all these are thermodynamic property. So when we are talking at the temperature, the pressure, viscosity, the volume, enthalpy, and all the rest, all these are thermodynamic property. Yeah, is defined as measurable characteristics of a system. Now, when you are working with as thermodynamic property is something you can't overemphasize when using Aspen Hysys. And from our previous, I need to, I want to reference, okay? Um, you see, we can translate a process into Aspen Hysys process simulation model by performing the following. Specify the components, specify the thermodynamic model to represent the physical properties of, and we said thermodynamic property is simply um, the measurable characteristics. So we are looking at one of the things we need to know is proper thermodynamic property that fits the model, that suits the process you are trying to simulate. The thermodynamic property of heavy hydrocarbon is actually different for that of a for that of light hydrocarbon. When you are um, running a simulation that involves soil water, electrolytes, all these are different properties. We are going to look at that. Okay, yeah. Thermodynamic model is a set of equations that permit the estimation of pure component and mixture property. In order to represent chemical processes, their modification, equipment, or new designs, the selection of a thermodynamic model that represents accurately the physical properties of the substance interacting in such process is mandatory. If you use the thermodynamic process or thermodynamic property or model that is supposed to be used, thermodynamic model that is supposed to be used for heavy hydrocarbon, if you use it for light hydrocarbon, you are not going to get an accurate result. There are four main groups of thermodynamic models available. One, we have the ideal model, we have the activity coefficient model, we have the equation of states, and we have special methods. We have special methods. Let's start with equation of state. Equation of state model, which is best for hydrocarbon and gas processing. Under equation of state, we have Penn Robinson. If you are working in the oil and gas, Penn Robinson is one of the most widely used models because it's best for hydrocarbon and more widely used in the oil and gas, handles vapor, liquid equilibria well for natural gas, crude oil, refinery, petrochemicals. It's accurate for non-polar and midly polar components. So we have the suave reddish squam, which is similar to PR, which is Ben Robinson, but better for light or hydrocarbon system. So you can see that have heavy hydrocarbon components, and you use this as alkane, you are going to get slightly different answer. Now, this is common in gas process, cryogenic, heavy what hydrocarbon. I said that. So that's why this first session, I'm dedicating it to explaining all this. You need to know the equation, the thermodynamic model relation. Then we also have modification of the Robinson with better accuracy for polar and associating compounds. Then next one, we have the activity coefficient model. is used for highly non-ideal liquids or non-ideal liquid system. We have polar. Um, Under the activity coefficient, we have NRTL, which is non-random to liquid, good for polar mixtures, agitate groups, and solvents, common in chemical and pharmaceutical worlds, industries. Now, if you are using NRTL for a hydrocarbon, just know that it doesn't matter if you are using the correct unit operations in your simulation, your answer is going to be wrong. It's more like you carrying out a mathematical, solving a problem, a mathematical problem, where the question that is asked is wrong. Even if you are using the right formula, your answer is wrong automatically. You are using the right formula, your step is correct, good, perfect change of subject, whatever you are doing, your step is correct, but the question is wrong. So definitely, automatically, your answer is wrong. And the moment you use the wrong, your simulation result is going to be wrong. Then you have Uniquark. Um, it handles highly non-ideal mixtures. So it says good for polar mixtures. We have Wilson suitable for highly non-ideal system with miscible gaps, with miscibility gaps. We also have the specialized property package tailored for specific application, like glycol property package, we have amine property package, we have electrolyte, NRTL, we have PRSV, and we have generalized model. And we have ID property package, we have leakage lab, blocker, and I dropped some rule of thumbs here. And when you are working with natural gas, crude oil, and refinery, these are the two equation thermodynamic model you can go for. Now, in order for you to pick from one of these, you automatically know that this SRK is for light crude or light hydrocarbon, and Ben Robinson best works for heavy hydrocarbons. Then when we are looking at gas processing, NLNG dehydration, we use SRK first, or now the reason we are SRK is coming first here, note, because gas processing, NLNG, are what liquid hydrocarbon. Yeah, when you're looking at amine sweetening, amine, we use amine property package. Glycol dehydration, we use glycol package. For electrolyte, acid, salt, we use electrolyte and RTL. For polar and azeotropic systems, e.g., ethanol water, acetone water, NRTL, Uniquark, Wilson, these are the packages we use for polar. Then for simple non-polar gases, we can use the Kessler blocker. Yeah. So in our next class, we are going to look at, I'm going to introduce you to Aspen Hysys, its interface, introduce you to, yes, to the Aspen Hysys simulation software. So we are going to see again our next class is going to be on Wednesday by 8:30 p.m. So please, if you have a question, I would like you to um, drop it in the comment section. I want to get your question, get your feedback. If you have a question, what have you. So please, if you haven't subscribed to this channel, I would like you to hit the subscribe button and subscribe to this YouTube channel. and also like. There's no question for today's session. We are going to see again on Wednesday, 8:30 p.m., where I'm going to introduce you to Aspen Hysys software. Thank you very much. See you next time.